this question is, I don't want you to get lost in this question in that you get confused by the situation and not what the idea is, right? It's a problem that involves measurement. Even though we use a metric system in Canada, a lot of things you buy are going to have measurements that are in imperial, right? Like if you go to buy a TV, this is the dimensions of most new TVs, right? You haven't been able to buy these kind of TVs for a while. The monitors on your tables right now, those computer monitors, are this proportion. They are 4 by 3, right? Because they're, if you measure the width and the height, that's the ratio that you get. But then widescreen TVs are this proportion. They're 16 by 9. They're 16, the ratio, if you divide the measurements, you get 16 by 9. All right? This problem involves you knowing something from grade 8 about the Pythagorean theorem. That's how I would approach it anyways. If you want to go through and work this out, basically you got to find the dimensions here, and then you can figure out the area, okay? It talks about the greater viewing area, which way. Okay, if you have a 32-inch TV that's that proportion or a 32-inch TV that's this proportion, which has the greater viewing area? I would do it just by using the known measurements here to get what the measurement is across there. If you have this triangle here, which I didn't trace very well, I'm going to draw a little triangle and the big triangle here. We know this is 32. But we don't know this. We're going to call this width and height. Okay, I'll call it width 1, height 1. And this one is 32. I'm going to call this width 2 and height 2 here. This is not necessarily how they do it in the book. This is how I would do it. If you know this one is 4 by 3, then you can draw that here. You can say, I'm going to draw a smaller triangle and I know it's 4 by 3. And you can use what you call similar triangles. And you can also use Pythagoras. You can work this side out if you know Pythagoras, the Pythagorean relationship. 3 squared plus 4 squared, what does that mean that other side should be? You don't have to write this down, but if you go 3 squared plus 4 squared equals that number squared, what is it supposed to be? Hypotenuse squared. Just call it x for now, x squared. You go down here and you find, I'll assume that you can do that, and you find that x is 5 here. Okay, so if you had a little TV that was 4 wide and 3 tall, it would be 5 on the diagonal. Once you know that, then you can work out the missing measurements pretty easily. Right? Because you have something to compare. You have a triangle where you know the diagonal, but not the other dimensions, and you have this. You can use a proportion. Okay? You can use a scale factor, right? Like if this is this, really I should have drawn it a lot smaller, right? Really it's about like that. It's a small little triangle, but you know all the dimensions. And you know one of the dimensions is this one, so you can work out the other ones. Right? If you know that this is, if you know how many times more that is, you divide those numbers and you can figure out how many times more it is. Should we divide those numbers and know the scale factor there? So if you divide 32 divided by 5, that scale factor is 6.4. Okay, so I'm going to say times 6.4. That's the scale factor for that TV. In other words, this is 6.4 times as big as this little triangle I drew here. So you can do the same with the other measurements then, right? This is going to be times 6.4, and this is going to be times 6.4. So drawing all those arrows is probably not very helpful, but if you want, every dimension is higher then. So you can say the width of this thing is 4 times 6.4. And the height of the thing is, let's figure this one out before we figure out the height. 6.4 times 4. Right, so it's 25.6. 25.6. And the height of this one is 3 times 6.4. Right? So you have 19.2. Then you got to work out the other ones, because that's all I need to be able to do is, once I have the dimensions of the thing, I can work out its area. Now, I haven't left myself enough room here, but I'll try anyways. The other one here, let's draw a little triangle that works for that one. If you have a little triangle here that has 9 and 16, a wider triangle than that. And you want to work out this hypotenuse. Again, I'm going to assume that you know the Pythagorean relationship. If you say this thing here, whatever we're going to call it now, we'll just call it m temporarily. M squared is 9 squared plus 16 squared. Let's pretend you know how to go down there and find that this is, what is it? What's 9 squared plus 16 squared, square root of that? Something crazy? What is it? Anybody tried it? Do you want me to do this for you? 9 squared plus 16 squared gives you that. And then we want square root of that number. Square root of 337. This number that's not so nice, 18.35 blah blah blah. 3576, let's call it. This is roughly 18.3576. Or you could just put 355 dot dot dot. I'm going to save that number here. I'm going to store this as M because that's what I called it. Then I can use that number again. That's what this thing is. Once I know that number, then I can work out the scale factor for this side. If you have the scale factor for this, if you know that this is roughly 18.36 and this is 32, okay, this is 32 here. Figure out the scale factor. If you divide those numbers, so I'm going to go 32 divided by that number, 18 point, that which I just called, I could actually just put answer here, not that. I can put answer. I can try again for a third time here. There we go. 32 divided by that number. So it's approximately 1.743 whatever. 1.743. That's the scale factor over here. Times 1.743 roughly. If I want the other numbers then, the other dimensions, the width and the height, that's just 16 times 16 times that number times 1.743, which is something. And then I got the other one, which is the height is 9 times 1.743. That gives me the two dimensions. Do that on the calculator here. So let's store that number as something. I'm going to store that as x. Easy to get to there. All right, so I have 16 times that number that I just stored. So that's the width of the thing, 27.9, roughly. 27.9. And that height is 9 times x, about 15.69, 15.7, 15.7. If I want the height on here, I can do that number times 15 point whatever times 27.89, let's call it. And that's going to give us our area. That's the area of the 16 by 9 television, 437 roughly. 438, 437.5. This is an involved question, you realize that. Area here of this TV is, multiply those two dimensions, right? This times this. So if I was going to do that, I'm running out of room here. 27.9 times 15.7. What did I say that was? 437? 437, whoops. 437.5 square inches. Whereas the other one here, if I'm going back over here to find the area of the other one here, let's move this out of the way here. So we have some more room. The area here is going to be the width times the height. Width 1 times height 1. Or in other words, if I multiply those two things, 25.6 times 19.2. Okay, on the calculator, what do I get here? 25.6 times 19.2. 491. 491.5. Okay, so that's the comparison. This one, the 4x3 television. I guess the answer to the question that says, which television has the greater viewing area? is the 4x3, the old-fashioned one. Okay, the old-fashioned one has a greater viewing area. Okay, let's zoom this down for a sec so we can see the whole question here. The older version has the greater viewing area for the same diagonal. Okay, think about what that means. This one is more square, right? If you look at the monitors on the table, they're more square than the thing like this. If you want the same area, you actually need a longer diagonal for a newer TV. So if you had an old one that was a 32-inch television, you might need a 34-inch television here to get the same area, if that makes any sense to you. All right? If it was a perfect square, I don't know, I mean, we don't have TVs as a perfect square, but if it was square, that would give you the most area for a 32-inch diagonal. Anyways, that's a fairly involved question, but that's how I would do it. I think maybe in the textbook they do it by a slightly different method, which is fine. There's lots of different ways to do it. Okay, but that involves two things: similar triangles and Pythagoras. Now, both those things are not involved in this unit, but you got to sometimes use things that you've learned in the past, right? This is just a problem that involves measurement. All right.